Read this script in a soft, gentle tone, perfect for a calm bedtime story. Use a natural American male voice that sounds like someone in his early 30s. Speak at a medium, natural conversational pace, not too slow and not too fast, similar to a comfortable audiobook. Gently slow down and add a short pause on the most important or emotional sentences, so each idea has time to land, but never drag the delivery. Make the narration casual, relaxed, and conversational, like a real American storyteller talking to a friend at the end of the day. Avoid sounding monotone. Use subtle changes in pitch, rhythm, and emphasis to keep it engaging, while always staying smooth, calm, and non-dramatic. Keep the voice slightly breathy and soothing, with small natural pauses between groups of sentences to help the listener relax, unwind, and fall asleep comfortably. The quiet hum of astronomy whispers the secrets of starlight from across unimaginable voids. These are some of the most amazing and relaxing facts about our cosmos. And if you enjoy this kind of bedtime listening for a good night's sleep, please consider liking and subscribing for more. There is no signpost or physical wall that marks where our atmosphere ends and outer space begins. Instead, humanity has agreed upon a conceptual boundary known as the Kármán line, floating 100 kilometers, or about 62 miles, above sea level. This isn't an arbitrary number. It represents a fascinating shift in physics. Below this line, a vehicle can stay aloft using aerodynamic lift generated by its wings pushing against the air. But as you ascend, the air becomes so incredibly thin that to achieve lift, you would need to travel at orbital velocity. The Kármán line is the altitude where the air is too sparse for aviation to function. To go any higher, a craft must rely entirely on astronautics, on the sheer thrust of rockets to escape Earth's pull. Crossing this invisible threshold is the official definition of becoming an astronaut, a quiet transition from being a creature of the sky to a voyager in the cosmos. Every time we look up at that cosmos, we are not seeing it as it is, but as it once was. This is due to a fundamental concept called look-back time. Light, while the fastest thing in the universe, still takes time to travel across the immense distances of space. We are perpetually living in the past of everything we observe beyond our own planet. The sunlight warming your face is over 8 minutes old, having made a 93 million mile journey to reach you. The light from our nearest stellar neighbor, Proxima Centauri, is from 4 years ago. And when you gaze upon the faint, misty patch of the Andromeda Galaxy, the closest major galaxy to our own, you are seeing light that began its journey 2.5 million years ago. Earth was then in the midst of the Ice Age, and early human ancestors roamed the planet. In this way, every telescope is a time machine, and every stargazer is a historian of the universe. This journey back in time has no single starting point because the universe has no center. The Big Bang was not an explosion that happened at one specific point in an existing empty space. Rather, it was an expansion of space-time itself, everywhere, simultaneously. A helpful way to imagine this is to think of the surface of an expanding balloon with dots drawn on it. From the perspective of any dot, all the other dots are moving away from it, but no single dot is the center of the balloon surface. In the same way, every galaxy in the universe is rushing away from every other galaxy. Observers in a distant galaxy would see our own Milky Way receding from them, making it seem as if they were at the center of the expansion. This profound idea means there is no privileged location in the cosmos. The origin of the universe is not a place you can travel to because it happened everywhere. What memory does the night sky evoke for you when you think about these vast ideas? The light carrying these cosmic stories travels at a speed that is famous for being a constant, but this is only true in the perfect vacuum of space. The ultimate speed limit, denoted as c, is approximately 299,792 kilometers per second. However, when light passes through a medium, anything from air to water to a diamond, it slows down. This happens because the photons of light are absorbed and re-emitted by the atoms within the material, a microscopic process that creates a delay. In water, light travels at about 75% of its vacuum speed, and through a diamond, it slows to less than half. In truly extraordinary laboratory experiments, physicists have managed to slow light down to a crawl, even bringing it to a complete halt for a moment by passing it through a cloud of ultra-cold atoms. This reveals that the universe's most famous constant is, in fact, beautifully variable, changing its pace as it journeys through different cosmic environments. While we can't see the beginning of the universe with our eyes, we can still detect its echo. This ancient signal is the cosmic microwave background, or CMB, a faint glow of radiation that permeates all of space. It is the residual heat from the Big Bang, a thermal afterglow from a time when the universe was a hot, dense plasma, just 380,000 years after its creation. As the universe expanded over billions of years, this primordial light stretched out, its wavelength lengthening from visible light into the microwave spectrum, cooling to a mere 2.7 degrees above absolute zero. For decades, a tiny percentage of the static, or snow, seen on old analog television sets between channels was actually this signal, a tangible connection to the dawn of time, humming quietly in the background of our daily lives. You were, in a very real sense, witnessing the leftover light from the birth of everything. The space between celestial objects, which seems so perfectly empty and black, is in reality not empty at all. This vacuum is a bustling, energetic place, teeming with activity on a quantum level. According to quantum field theory, this void is filled with what are known as virtual particles, pairs of particles and antiparticles that spontaneously pop into existence from borrowed energy, exist for a fraction of a second, and then annihilate each other. Beyond this quantum foam, interstellar and intergalactic space is also filled with a thin soup of stray atoms, mostly hydrogen and helium, as well as cosmic rays, neutrinos, and elusive dark matter. The average density is incredibly low, perhaps only a few atoms per cubic meter, but it is far from being a true nothingness. The great emptiness of space is less an absence of substance and more a vast, near imperceptible ocean of fleeting particles and ancient wandering atoms. Because of the finite speed of light, there is a hard limit to how much of this vast universe we can ever see. This boundary defines the observable universe, a spherical region centered on us with a radius of about 46.5 billion light-years in every direction. This doesn't mean the universe is 93 billion light-years across. It's just the distance light from the most remote objects has had time to travel to reach Earth since the Big Bang began 13.8 billion years ago. The reason the radius is so much larger than 13.8 billion light-years is that the space through which the light was traveling has been continuously expanding all that time. We have no way of knowing what lies beyond this cosmic horizon. The full universe could be hundreds of times larger, or even infinite. We are, in essence, on an island in a cosmic ocean, able to see only the shores that are close enough for their light to have reached us. The grand architect of this cosmic structure is gravity, but not in the way we typically imagine it. Albert Einstein's theory of general relativity reframed our understanding of it entirely. Gravity is not a mysterious force pulling objects toward one another across empty space. Instead, it is a consequence of the curvature of space-time itself. Massive objects like stars and planets warp the four-dimensional fabric of space-time around them, much like a heavy bowling ball placed on a stretched-out rubber sheet. Other, smaller objects, like planets orbiting a star, are not being pulled by a force. They are simply following the straightest possible path, called a geodesic, through this curved spacetime. The Earth orbits the Sun for the same reason a marble will circle the dip made by the bowling ball. It is an elegant and profound dance, where matter tells spacetime how to curve, and curved spacetime tells matter how to move. If you could somehow gather up all the light from all the stars and galaxies across the entire observable universe and mix it all together, what color would you get? It wouldn't be the deep black we associate with space, nor the vibrant blue of a young star. Instead, the average color of the universe is a gentle, unassuming shade of beige. In 2002, astronomers at Johns Hopkins University averaged the light from over 200,000 galaxies to determine this cosmic hue. After an initial miscalculation that suggested a pale turquoise, they corrected their findings and settled on a color they whimsically named Cosmic Latte. This beige tone is the result of a long history. In the distant past, when most stars were young, hot, and blue, the universe's average color would have been much bluer. As stars have aged, more red and yellow giants have come to dominate, shifting the cosmic palette toward this warm, creamy off-white. Measuring the staggering distances to these colorful galaxies would be impossible without a clever astronomical tool known as a standard candle. These are celestial objects that have a known, consistent intrinsic brightness, or luminosity. Just as you can estimate the distance to a 100-watt light bulb by observing how dim it appears, astronomers can do the same with these cosmic beacons. The most famous and reliable standard candles are Type Ia supernovae. These are spectacular explosions that occur when a white dwarf star in a binary system pulls too much matter from its companion and reaches a precise critical mass, always exploding with almost the exact same peak luminosity. By comparing this known absolute brightness to the apparent brightness we see from Earth, astronomers can calculate the distance to the supernova's host galaxy with incredible precision. These explosive events are the cosmic measuring tapes that allow us to map the universe. Deep within the Sun's core, a constant, silent storm of fusion reactions is taking place. And with every flicker of this atomic fire, countless ghost-like particles called neutrinos are born. Right now, as you listen, trillions of these solar neutrinos are passing through your body, through the bed you're resting on, and through the entire Earth itself, as if none of it were even there. They are so incredibly elusive and interact so weakly with matter that for decades, scientists were baffled. Their instruments on Earth could only detect about a third of the neutrinos they predicted the Sun should be making. This was known as the solar neutrino problem. The mystery was only solved when it was discovered that neutrinos can change their flavor or type during their 8-minute journey from the Sun to Earth. They weren't missing, they were simply arriving in disguise, a shape-shifting act across 93 million miles of space that revealed a profound new layer of particle physics. And while these particles travel in silence, the Sun itself is anything but quiet. It is filled with a deep, resonant sound. The entire star vibrates like a colossal bell, humming with sound waves that are trapped within its fiery plasma. This field of study, known as helioseismology, allows astronomers to study the Sun's hidden interior by listening to its surface oscillations, much like a geologist uses seismic waves to understand Earth's core. These sound waves are at a frequency far, far too low for the human ear to perceive, but if we could somehow translate and amplify them, the sun would produce a deafening, continuous roar. It is a constant, low-frequency song of creation, a cosmic hum generated by the turbulent convection currents of energy rising and falling within our star, a sound that has filled our solar system for over 4.5 billion years. Traveling from this humming star to its closest companion, we find a world of impossible contrasts. Mercury, the smallest planet, endures the sun's most ferocious glare, with daytime temperatures soaring to over 800 degrees Fahrenheit, hot enough to melt lead. Yet, nestled within craters near its poles, there are regions of perpetual darkness. Because Mercury has almost no axial tilt, the floors of these deep craters have not seen a single ray of sunlight in billions of years. In these pockets of absolute shadow, temperatures plummet to hundreds of degrees below zero. NASA's Messenger spacecraft confirmed that these unimaginably cold, dark places hold vast deposits of water ice, perhaps several meters thick. It is a stunning paradox of astronomy. One of the hottest places in the solar system is also home to ancient, frozen water, preserved for eons simply by hiding in the planet's own permanent shadow. This little world of fire and ice is also slowly shrinking. Mercury is distinguished by a massive, dense iron core that makes up an unusually large percentage of its total volume. As this enormous core has gradually cooled and contracted over billions of years, the planet's entire crust has been forced to buckle and compress around it. This shrinking process has created a unique geological feature all over its surface, enormous cliffs and ridges called lobate scarps. These are not gentle hills. They are towering, winding escarpments, some of which stretch for hundreds of miles and rise more than a mile high. They are essentially planetary wrinkles, ancient stress marks etched into the crust that tell the story of a planet slowly pulling itself inward, a geological record of its long, cooling history written across its face like the lines on a clenched fist. From a shrinking world, we journey outward to one that seems to move in slow motion. On the planet Venus, a single day is longer than an entire year. It takes Venus a staggering 243 Earth days to complete just one rotation on its axis, the slowest spin of any planet in our solar system. In contrast, it completes its orbit around the Sun in only 225 Earth days. This creates a bizarre reality where the Venusian year passes by before the Venusian day is even over. To make things even stranger, Venus spins backwards. On almost every other planet, including our own, the Sun rises in the east and sets in the west. But on Venus, due to its retrograde rotation, the Sun would appear to rise in the west and slowly make its way across the sky to set in the east. A lazy, reversed journey that takes hundreds of our days to complete. This slow, backward world is shrouded in a toxic and crushing atmosphere, creating the most extreme greenhouse effect known. Composed almost entirely of carbon dioxide, with thick, swirling clouds of sulfuric acid, the Venusian atmosphere traps heat so effectively that the surface temperature is a uniform 900 degrees Fahrenheit, hotter even than Mercury. It's so hot that lead would exist as a puddle on the ground. High above this infernal landscape, in the upper reaches of the Venusian mountains, something truly extraordinary occurs. The atmospheric pressure and temperature are just right for certain vaporized metals to condense and fall back to the surface. Scientists believe that the shimmering radar reflections seen on Venus's highest peaks are actually a delicate frost or snow made of heavy metals, likely lead sulfide and bismuth sulfide. On the highest mountains of Venus, it literally snows metal. Let's turn our attention homeward to our own planet and its faithful companion. Our moon, the anchor of our night sky and the keeper of our tides, is slowly but surely leaving us. Every year, the moon inches away from Earth by about 3.8 centimeters, or roughly 1.5 inches, about the same rate at which your fingernails grow. This steady retreat is caused by the transfer of rotational energy from the Earth to the moon through tidal forces. Billions of years ago, the moon was much closer, appearing enormous in the sky, and a day on Earth was only a few hours long. As it has drifted away, it has pulled on Earth's rotation, slowing our day down to the 24 hours we now know. In the unimaginably distant future, the moon will appear smaller in our sky, and a perfect total solar eclipse will no longer be possible. Our planet's relationship with the cosmos also dictates its climate in a slow, hypnotic rhythm. Earth does not spin like a perfect top. It has a slight wobble in its rotation, known as axial precession. This gentle wobble, combined with gradual changes in the tilt of its axis and the shape of its orbit around the Sun, creates a series of overlapping cycles known as Milankovitch cycles. These are cosmic pacemakers, operating on timescales of tens of thousands to hundreds of thousands of years. They subtly alter the distribution and intensity of solar radiation reaching different parts of the Earth's surface. Scientists have found that these long, predictable astronomical cycles are the primary driver of our planet's ice ages, a gentle celestial nudge that can plunge the world into deep freezes or warm it into interglacial periods like the one we are in today. Moving outward to our final inner planet, we find a world that once housed geological titans. Mars is home to the largest volcano ever discovered in the solar system, a colossal shield volcano named Olympus Mons. It stands at a staggering height of nearly 13.6 miles, or 22 kilometers, making it almost 3 times taller than Mount Everest. Its base is so immense, covering an area roughly the size of France, that its slope is actually very gradual. If you were standing at the foot of this Martian giant, its peak would be so far away that it would lie completely beyond the horizon, hidden by the curvature of the planet itself. The volcano was able to grow to such an epic scale because Mars has much lower surface gravity than Earth and, crucially, lacks tectonic plates, meaning the crust remains stationary over a magma hotspot for hundreds of millions of years. Perhaps the greatest mystery of Mars is its profound and starkly divided surface. The planet is essentially a world of two halves. The southern hemisphere is a rugged, ancient landscape, heavily pockmarked with craters and sitting at a much higher elevation. In dramatic contrast, the northern hemisphere is remarkably smooth, geologically younger, and lies several miles lower in elevation. This sharp division is known as the Martian dichotomy. For decades, scientists have debated its cause, with the leading theory proposing a cataclysmic origin. Early in its history, Mars may have been struck a glancing blow by a massive object, perhaps the size of Pluto. This colossal impact would have blasted away the entire northern crust, creating a gigantic basin that may have later filled with water, forming a primordial Martian ocean. Jupiter's Great Red Spot, a storm so vast it could swallow our Earth whole, is not just a surface feature. It is a terrifyingly deep vortex, plunging at least 300 miles, or 500 kilometers, into the planet's atmosphere. This is far deeper than the International Space Station's orbit above us, a storm with roots that extend further down than the entire vertical expanse of Earth's own atmosphere. For comparison, the deepest part of our ocean, the Mariana Trench, is only about 7 miles deep. This crimson-hued anticyclone has been observed for at least 200 years, and possibly for more than 350, making it a centuries-old tempest of unimaginable scale and endurance. Yet, this ancient storm is slowly changing. Recent observations show it is becoming smaller and more circular, a sign that even the most powerful phenomena in our solar system are not eternal. The winds at its edge still rage at over 400 miles per hour, but its fate remains a profound mystery, a slow, cosmic drama playing out across the gas tops of a giant world. The source of Jupiter's immense power is hidden deep within, where pressures are so extreme they crush hydrogen gas into a liquid metal. This vast, spinning ocean of metallic hydrogen acts as a colossal dynamo, generating the most powerful magnetic field of any planet in our solar system. It is nearly 20,000 times stronger than Earth's, creating a magnetosphere so large that, if it were visible in our night sky, it would appear larger than the full moon. This magnetic bubble is a deadly environment, trapping charged particles from the solar wind and accelerating them to incredible speeds, forming intense radiation belts that would be lethal to any unprotected astronaut. The beautiful, dancing auroras at Jupiter's poles are a visible manifestation of this power, a constant, silent light show driven by a force that shields the planet but makes it one of the most hazardous places we know. Saturn's rings, which appear as a solid, elegant structure from a distance, are in reality a celestial illusion of unimaginable delicacy. They are composed of countless individual particles of water, ice, and rock, ranging in size from microscopic dust grains to chunks as large as mountains. This vast, shimmering disk stretches over 175,000 miles from end to end, yet it is astonishingly thin. In most places, the rings are only about 30 feet, or 10 meters, thick. This incredible ratio of width to thickness makes them proportionally thinner than a sheet of paper. If you were to build a scale model of Saturn 1 meter wide, its rings would be 10,000 times thinner than a razor blade. This ethereal structure is not a permanent feature. It is a dynamic system, constantly sculpted by the gravity of Saturn's many moons, and slowly raining its icy particles down onto the planet, destined to disappear completely in a few 100 million years. At Saturn's North Pole spins a weather pattern unlike anything else seen in the solar system, a colossal, six-sided jet stream known as the hexagon. This perfectly formed geometric storm is so immense that 2 planets the size of Earth could fit inside it. While hurricanes on Earth are born from warm ocean water and last for weeks, Saturn's hexagon has remained stable for decades, if not centuries. It is not a conventional storm, but a persistent wave in the jet stream, rotating almost in perfect sync with the planet's own rotation. Scientists believe it is a manifestation of deep atmospheric flows, a pattern etched into the clouds by unseen currents far below. Within this bizarre structure, smaller vortices rotate and winds whip around at over 200 miles per hour, a strangely orderly piece of chaos in an atmosphere of swirling golden haze. Uranus travels through space on its side, a fallen giant rolling through its orbit. It has the most extreme axial tilt of any planet, a staggering 98 degrees. This means its north and south poles lie where most planets have their equators. The cause is thought to be a massive collision with an Earth-sized protoplanet early in its history, an impact that literally knocked the world over. This peculiar orientation results in the most bizarre and extreme seasons in the solar system. For a quarter of its 84-year orbit, one pole is bathed in continuous, unending sunlight, while the other faces 2 decades of absolute darkness and cold. Then, as it continues its journey, the situation slowly reverses. These long, dark winters and endless summers shape a world of profound contrasts, a cycle of light and shadow stretched across a lifetime. Does the thought of a winter that lasts for 21 years feel more peaceful or unsettling to you? While one might expect the most distant planet, Neptune, to be the coldest, that title actually belongs to Uranus. Despite being over 1 billion miles closer to the Sun than its neighbor, Uranus has the coldest planetary atmosphere ever recorded in our solar system, with temperatures dropping to a bone-chilling -224 degrees Celsius or -371 degrees Fahrenheit. This is colder than solid nitrogen. The reason for this intense cold is a long-standing puzzle. Most giant planets, including Jupiter, Saturn, and Neptune, radiate significantly more heat from their cores than they receive from the Sun. Uranus, however, barely radiates any internal heat at all. It's as if its primordial heat from formation was lost or is somehow trapped deep inside, unable to escape. This lack of an internal engine makes its upper atmosphere a place of deep, profound, and unexpected cold. The serene, blue appearance of Neptune belies a world of unimaginable violence. It is home to the fastest and most ferocious winds in the entire solar system. These winds, primarily composed of hydrogen, helium, and methane, whip through the planet's upper atmosphere at speeds exceeding 1,200 miles per hour, or 2,000 kilometers per hour. That is faster than the speed of sound on Earth. These supersonic jet streams carry massive storm systems, like the Great Dark Spot observed by Voyager 2, a colossal anticyclone the size of Earth that was torn apart and vanished within a few years. Unlike storms on Earth, which are powered by the Sun, Neptune's furious weather is driven by its own internal heat source. The planet radiates more than twice the energy it receives from the distant Sun, a powerful internal engine that churns its atmosphere into a tempestuous supersonic frenzy. Neptune's discovery was not made with eyes, but with minds. It was the first planet to be found through mathematical prediction rather than direct observation. By the 1840s, astronomers had noticed that the planet Uranus was not following its predicted orbit precisely. It was being tugged by the gravity of an unseen object. The French mathematician Urbain Le Verrier, using only pen, paper, and the laws of Newtonian physics, calculated the exact position of this mysterious eighth planet. He sent his predictions to the Berlin Observatory, and on the very first night of searching, September 23, 1846, astronomers Johann Galle and Heinrich d'Arrest pointed their telescope to the specified location. There, less than 1 degree from where Le Verrier had predicted, was a small blue disk. It was Neptune, a world discovered not by chance, but by the sheer power of human intellect and the universal language of mathematics. On the distant surface of Pluto lies one of the most beautiful and surprising features in our solar system, a vast, bright, heart-shaped glacier. This feature, named Tumba Regio in honor of Pluto's discoverer, is not made of water ice, but of a soft, exotic mixture of frozen nitrogen, methane, and carbon monoxide. The western lobe of this heart, a smooth, crater-free plain called Sputnik Planitia, is a massive basin filled with these ices. It is not a static, dead landscape. Evidence shows that this glacier is geologically active, with the soft nitrogen ice slowly churning in a process of convection, similar to the wax in a lava lamp. Huge polygons of ice, miles across, are pushed up from below, slowly renewing the surface over millions of years. This gentle, constant motion, driven by Pluto's faint internal heat, erases impact craters and paints a fresh, youthful heart on the face of this tiny, frozen world. The demotion of Pluto from its status as our ninth planet was not an isolated decision, but the result of a discovery that revealed a new, crowded frontier in our solar system. That discovery was Eris, a dwarf planet orbiting in the scattered disk far beyond Neptune. When it was first identified in 2005, initial measurements suggested it was larger than Pluto, sparking a fierce debate about the very definition of a planet. If Pluto was a planet, then surely Eris had to be one as well, and perhaps dozens more icy worlds lurking in the darkness. Eris is now known to be slightly smaller than Pluto in diameter, but it is about 27% more massive, meaning it is made of much denser rock and ice. Its discovery was the final catalyst that forced the International Astronomical Union to formally define what it means to be a planet, ultimately leading to the creation of the dwarf planet category and a profound reshaping of our solar system map. Beyond the grand orbits of the planets lie countless smaller worlds, each with a story of fire, ice, or ancient collision. Neptune's largest moon, Triton, is one such world, a true outlier in our solar system. It is the only large moon to orbit its planet in a retrograde direction, meaning it circles Neptune backwards compared to the planet's rotation. This is a telltale sign that Triton was not born alongside Neptune, but was a dwarf planet, much like Pluto, that wandered too close and was captured by Neptune's immense gravity. This violent capture likely melted its interior, creating a dynamic world that is still active today. Instead of fiery volcanoes, Triton hosts cryovolcanoes. These icy vents erupt plumes of liquid nitrogen, methane, and dust, which then freeze in the frigid air and fall back to the surface as a dark nitrogen frost. These dark streaks, visible against the moon's pinkish, cantaloupe-like terrain, are evidence of an ongoing alien geological process powered by a past that was anything but peaceful. While Triton's activity is driven by ice and cold, another moon is a realm of unimaginable fire. Jupiter's moon Io is the most volcanically active body in the entire solar system, a world constantly tearing itself apart from the inside out. Its surface is a chaotic canvas of yellows, reds, and blacks, painted by sulfur in its many forms. It has no impact craters, as its surface is constantly being paved over by fresh lava flows. This relentless volcanism is not powered by remnant heat from its formation, but by a process called tidal heating. As Io orbits the giant Jupiter, the planet's immense gravity pulls on it. This pull is not uniform. It's made uneven by the rhythmic gravitational tugs of the other large Jovian moons, Europa and Ganymede. This constant gravitational war of tugs causes Io's solid body to bulge and flex by as much as 100 meters. The friction from this relentless kneading generates incredible heat in its interior, keeping its mantle molten and powering hundreds of volcanoes that spew plumes of sulfur and gas hundreds of kilometers into space. Remaining in the realm of Saturn's moons, we find a world that hides its secrets far better than Io. Mimas, a small inner moon, is most famous for the enormous Herschel crater that dominates one hemisphere, giving it an uncanny resemblance to the Death Star from science fiction. For decades, it was considered a simple, frozen, and geologically dead chunk of ice and rock. However, data from the Cassini spacecraft revealed a profound anomaly in its orbit, a peculiar wobble or libration that was too large to be explained by a solid, uniform body. Scientists were left with two astonishing possibilities. Either Mimas has a core shaped like a flammed football, or, far more likely, it is a stealth ocean world. This theory suggests that beneath its ancient, cratered ice shell, between 20 and 30 kilometers thick, lies a global ocean of liquid water. If true, Mimas would represent a new class of ocean moon, one that shows no outward signs of its inner ocean, forcing us to rethink where liquid water might be hiding in our solar system and beyond. Moving away from the moons that hug their planets, we find the scattered remnants of planetary formation in the asteroid belt. Popular culture often depicts this region between Mars and Jupiter as a dense, chaotic field of tumbling rocks that requires incredible skill to navigate. The reality of this part of our solar system is profoundly different and much emptier. The asteroid belt is so vast and its contents so spread out that if you were standing on any given asteroid, you likely wouldn't be able to see another one with the naked eye. The average distance between major asteroids is over 1 million kilometers, more than twice the distance from the Earth to the Moon. Spacecraft like Pioneer and New Horizons have flown through the belt without any course corrections, their chances of an accidental collision being infinitesimally small. In fact, the total mass of every single object in the asteroid belt combined is only about 4% of the mass of Earth's moon. It's less a cosmic gravel pit and more a celestial desert. The undisputed king of this celestial desert is Ceres, an object so large it contains 1/3 of the entire mass of the asteroid belt. Once considered the largest asteroid, it has been reclassified as a dwarf planet, the only one in the inner solar system. What makes Ceres truly remarkable, however, are the mysterious, dazzlingly bright spots that pepper its dark surface. The most famous of these, located in Akator crater, are known as Cerealia Facula and Venalia Faculae. For years, scientists speculated they were exposed ice, but close-up observations from the Dawn mission revealed they are something even more fascinating: vast deposits of sodium carbonate, a type of salt. This strongly suggests that Ceres once had, and may still have, a subsurface reservoir of briny water. This mineral-rich water is thought to have welled up to the surface through fractures, sublimating into space and leaving behind these brilliant salt flats, a sign of a complex and geologically active past on a world far from the sun. Further out still are the icy travelers of the solar system, the comets. When we picture a comet, we typically imagine a bright head followed by a long, graceful tail. But nearly every comet that approaches the sun displays not one, but 2 distinct tails, each formed by a different process and pointing in a slightly different direction. The first, and more visually obvious, is the dust tail. As solar radiation heats the comet's nucleus, it releases gas and dust. The relatively large dust particles are gently pushed away by the pressure of sunlight itself, forming a broad, diffuse, and often curved tail that tends to follow along the comet's orbital path. The second, more ethereal tail is the ion tail. This one is made of gas from the comet that has been stripped of electrons, or ionized, by the sun's ultraviolet light. These charged particles are then grabbed by the solar wind and pushed directly and forcefully away from the sun, creating a narrower, straighter tail that often glows with a faint blue light. This means the ion tail acts like a cosmic windsock, always pointing directly away from the sun, no matter which way the comet is moving. These comets have to come from somewhere, and their origin points to the true, vast boundary of our solar system. Beyond the Kuiper belt lies a theoretical, immense sphere of icy bodies known as the Oort cloud. It has never been directly observed, as its objects are too small, dark, and distant. Its existence is inferred from the orbits of long-period comets, those with orbital periods of thousands or even millions of years. Unlike objects from the Kuiper belt, which orbit on a relatively flat plane like the planets, these comets arrive from every conceivable direction and angle. This suggests their home is not a disk, but a vast spherical shell surrounding the entire solar system. The scale of the Oort cloud is difficult to comprehend. It is thought to begin about 2,000 times farther from the sun than the Earth, and may extend up to a light year away, a quarter of the distance to the nearest star, Proxima Centauri. At this profound distance, these icy bodies are only tenuously held by the sun's gravity, where the slightest nudge from a passing star can send one on its long journey inward. While the Oort cloud remains theoretical, the Kuiper belt is a region we have begun to explore directly. One of its most fascinating residents is a small object named Arrokoth, which was visited by the New Horizons spacecraft after its flyby of Pluto. Arrokoth provided humanity its first close-up look at a pristine, primordial object from this distant region. It has a remarkable shape, resembling two flattened, reddish pancakes gently fused together. This structure is known as a contact binary, and it tells a beautiful story about the dawn of the solar system. The two lobes that make up Arrokoth likely formed near one another, and, over millions of years, their mutual gravity slowly drew them together. They eventually touched, not in a violent collision, but with a whisper-soft impact, at a speed no faster than a gentle walking pace. They merged without shattering, preserving their original forms. Arrokothus is therefore an undisturbed relic, a 4.5 billion-year-old fossil from the era when the building blocks of planets were just beginning to come together. The Kuiper belt is home to other oddities, including the dwarf planet Haumea, which defies the expectation that large bodies should be spherical. Haumea is one of the strangest known objects of its size, shaped like a stretched-out American football. This extreme elongation is the result of its staggeringly fast rotation. It completes a full spin in just under 4 hours. This is so fast that it has literally flung itself into this oblong shape. It is believed that a massive collision in the distant past sent Haumea spinning so wildly. As if its shape weren't enough, astronomers were stunned to discover in 2017 that Haumea has its own system of rings. This made it the first and, so far, only dwarf planet known to possess rings, and the most distant ringed object ever discovered in our solar system. The rings are thought to be composed of icy debris that was blasted off Haumea during that same ancient cataclysmic impact that set it spinning, a delicate cosmic halo around a truly unique world. Returning one last time to Saturn, we find a moon that combines many mysteries into one. Iapetus is a world of stark duality, famous for its two-tone coloration. Its leading hemisphere, the side that faces forward in its orbit, is as dark as asphalt, while its trailing hemisphere is as bright as pristine snow. This sharp yin-yang divide is thought to be caused by a cosmic spray painting effect. Saturn's distant dark moon Phoebe orbits in the opposite direction, shedding a faint trail of dust. As Iapetus plows through this dust cloud, its leading face gets coated in this dark material. The darkened surface then absorbs more sunlight and heats up, causing any ice to sublimate away and leaving behind an even darker, concentrated residue. But the strangeness doesn't end there. Encircling the moon's equator is a colossal mountain range, some 13 kilometers high and 20 kilometers wide, running almost perfectly along its midline. This massive equatorial ridge gives Iapetus the appearance of a walnut, and its origin remains one of the great unsolved puzzles of planetary science. While most stars we imagine are similar to our Sun, the universe is home to true behemoths that defy comprehension. The most massive star currently known to us is called R136a1, a colossal object located in the Large Magellanic Cloud. This single star contains the mass of roughly 265 of our suns, yet it is only about 30 times wider. This incredible density means it burns through its fuel at a furious rate, shining with a luminosity nearly 9 million times greater than the Sun. If you were to replace our Sun with R136a1, its sheer radiative power would make Earth's surface hotter than the Sun's current surface, and its intense ultraviolet radiation would render life impossible. These ultra-massive stars are exceptionally rare and have incredibly short lifespans, burning for only a few million years before they exhaust their fuel. They live fast and die young, ending their lives in spectacular explosions that enrich the cosmos with heavy elements, seeding the next generation of stars and planets. The very existence of such a star challenges our models of star formation, as it's difficult to explain how so much mass can accumulate in one place without blowing itself apart during its formation. As these massive stars age, some undergo a dramatic transformation into a rare and violent phase known as a Wolf Rayet star. These are evolved, massive stars, typically over 20 times the mass of our Sun, that have completely blown away their outer layers of hydrogen. This process exposes their intensely hot inner core, which is rich in helium and heavier elements like carbon and nitrogen. With surface temperatures soaring between 30,000 and 200,000 Kelvin, they are among the hottest stars known. What makes them truly spectacular are their powerful stellar winds, which rush outwards at speeds of thousands of kilometers per second. This isn't a gentle solar breeze, it's a constant, furious expulsion of mass, causing the star to lose the equivalent of Earth's mass every single year. This shed material creates beautiful, intricate nebulae around the star, glowing as they are energized by its fierce ultraviolet light. A Wolf Rayet star is a star in its death throes, a beautiful but fleeting spectacle that will last only a few 100,000 years before it finally collapses and explodes as a brilliant supernova. The end for the most massive of these stars may not be a mere supernova, but something far more cataclysmic known as a hypernova. A hypernova, sometimes called a collapsar, is a theoretical explosion believed to be at least 10 times more energetic than a standard supernova. It is thought to occur when a star with more than 30 times the mass of our Sun collapses at the end of its life. Unlike a normal supernova, where the core collapses into a neutron star, the core of a hypernova candidate is so massive that it collapses directly into a black hole. As surrounding material frantically swirls into this newborn black hole, it forms an accretion disk that launches two incredibly powerful jets of plasma from its poles. These jets travel at nearly the speed of light, blasting through the outer layers of the star and into space. If one of these jets were aimed directly at Earth, it could be responsible for what we call a long-duration gamma-ray burst, one of the most energetic phenomena in the universe. A single hypernova can release more energy in a few seconds than our Sun will in its entire 10 billion-year lifetime. In stark contrast to these violent giants, the universe is overwhelmingly dominated by small, quiet stars known as red dwarfs. These are the most common type of star in the Milky Way, making up an estimated 75% of the stellar population, yet not a single one is visible to the naked eye from Earth due to their extreme dimness. A typical red dwarf has only a fraction of the Sun's mass, somewhere between about 8 and 50%. Because of their low mass, the pressure and temperature in their cores are much lower, causing them to fuse hydrogen into helium at a tremendously slow rate. This leisurely pace of fusion means they have extraordinarily long lifespans. While our Sun will live for about 10 billion years, a red dwarf can live for trillions of years. This is so long, in fact, that the universe, at only 8 billion years old, is still in its infancy from their perspective. Not a single red dwarf has yet had enough time to progress beyond its main sequence phase. Every red dwarf that has ever been created is still shining, patiently sipping its fuel.
Because no red dwarf has ever reached the end of its life, their ultimate fate is purely theoretical. a story that will unfold in the far, far distant future of the cosmos. Unlike a massive star that ends in a supernova, or a sun-like star that swells into a red giant, a red dwarf is not massive enough for either fate.
As it slowly burns through its hydrogen fuel over trillions of years, it will gradually heat up and become smaller and bluer. At this stage, it is hypothesized to become a blue dwarf, a type of star that does not yet exist in our young universe. This phase would last for billions of years before its fuel is finally completely exhausted. With fusion ceasing forever, the star will no longer be able to support itself against gravitational collapse. It will shrink and cool down, fading into a helium-white dwarf. This object, a dense ball of degenerate matter, will then spend countless eons slowly radiating away its remaining heat, eventually becoming a cold, dark black dwarf, a silent, stellar ember drifting through the darkness of a dying universe. Between the familiar stellar types lies a realm of strange and theoretical objects, and perhaps none is more bizarre than the Thorne-Zhitkov object. This is a hypothetical type of star first proposed in the 1970s by physicists Kip Thorne and Anna Zhitkov that is essentially a star within a star. It's theorized to form when a compact neutron star, the incredibly dense remnant of a supernova, collides with and is absorbed by a massive companion star, typically a red giant or supergiant. Instead of the collision causing an explosion, the neutron star sinks down to the core of the larger star. There, it disrupts the normal fusion processes. The red giant's core is effectively replaced by the neutron star, and the object's energy now comes from the accretion of material from the giant's envelope onto the neutron star's surface. From the outside, a Thorne-Zhitkov object would look almost identical to a normal red supergiant, but its chemical signature would be completely different, showing an overabundance of heavy elements created by the unique nuclear processes occurring deep within, near the surface of the embedded neutron star. While we have found candidates, their existence remains unconfirmed, a truly ghostly and fascinating possibility in stellar astronomy. Shifting from the theoretical to the observable, some stars stand out for their breathtaking color. Carbon stars are a rare class of giant stars, similar to red giants, but with a remarkable chemical anomaly in their atmospheres. In most stars, including our Sun, the atmosphere contains more oxygen than carbon. In a carbon star, this balance is flipped. Through processes deep within their interiors, carbon dredged up from the core has enriched their outer layers, making it more abundant than oxygen. This seemingly small change has a dramatic effect on the star's appearance. The excess carbon atoms readily combine to form molecules like dicarbon and silicon carbide, which are very effective at absorbing blue and yellow light. This leaves predominantly red light to pass through, giving these stars a spectacular, deep ruby red color, making them some of the most vividly colored objects in the night sky. These carbon-rich molecules eventually form a dark, sooty dust in the star's cool outer atmosphere, which is then blown out into space by strong stellar winds, creating a kind of cosmic smog and seeding the interstellar medium with the building blocks of future planets and even life. Some stars are not constant in their brightness, but pulsate with a reliable clockwork rhythm. Among the most important of these are the Cepheid variables. These are giant and supergiant stars that have moved past their main sequence lifetime and have begun to swell. Their interiors have become unstable, causing them to physically expand and contract in a predictable cycle that can last from days to months. As the star expands, its surface cools and becomes dimmer. As it contracts, it heats up and becomes brighter. The truly amazing discovery made by Henrietta Leavitt in the early 20th century was that a Cepheid's pulsation period is directly linked to its true intrinsic brightness.
The longer it takes to pulse, the more luminous the star actually is.
This period luminosity relationship turns Cepheid variables into one of the most crucial tools in astronomy. By measuring the pulsation period of a distant Cepheid, we can determine its true brightness. By comparing that to how bright it appears from Earth, we can calculate its distance with incredible accuracy, turning these pulsating stars into standard candles for measuring the vastness of the universe. There exists a class of celestial objects that blurs the very line between a star and a planet. These are the brown dwarfs, often called failed stars. They form in the same way as stars, from the gravitational collapse of a dense cloud of gas and dust, but they never accumulate enough mass to ignite sustained hydrogen fusion in their cores, the process that defines a true star. To be considered a star, an object needs at least 80 times the mass of Jupiter. Brown dwarfs fall into a mass range between about 13 and 80 Jupiters. While they can't fuse regular hydrogen, the most massive brown dwarfs are hot and dense enough to briefly fuse deuterium, a heavier isotope of hydrogen. This provides them with a temporary source of energy, allowing them to glow faintly, not with the brilliant light of a star, but with a dim, ruddy light, shining mostly in the infrared spectrum. After their deuterium supply is exhausted, they simply cool and fade over time. They are cosmic loners, wandering the galaxy in darkness, far more numerous than the stars we can see, but hidden from our view unless we look with infrared eyes. Finally, we turn our gaze toward the future of our very own home star, the Sun. It will not end its life in a violent supernova. It simply isn't massive enough. Instead, it will follow the much more common path of a low-mass star. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core. With the outward push of fusion ceasing, the core will begin to contract and heat up under its own gravity. This will cause a shell of hydrogen around the core to ignite, and the star's outer layers will begin to expand dramatically. The Sun will swell into a red giant, its diameter increasing by a factor of over 200, engulfing Mercury, Venus, and almost certainly Earth. After this phase, the helium core will eventually ignite in a helium flash, and the Sun will shrink for a time before expanding again. Eventually, its gravitational pull will become too weak to hold on to its bloated outer layers. They will drift away into space, forming a beautiful, glowing shell of gas known as a planetary nebula. At the center, the hot, dense core of the Sun will be left behind, a white dwarf, a final, fading ember about the size of Earth. It's a humbling thought, imagining the final, quiet chapter of our own solar system. As you settle into your sleep tonight, does thinking about these vast, cosmic timescales make your own daily worries feel a little smaller? Let me know your thoughts in the comments when you wake. The iconic pillars of creation within the Eagle Nebula are not being destroyed by the brilliant young stars above them, but rather they are being revealed. It's a common thought to see the searing ultraviolet light from the massive stars as a purely destructive force, blasting away at these majestic columns of gas and dust. But the process is more like a celestial sculpture being slowly unveiled. This intense radiation is evaporating the less dense outer layers of the clouds, a process called photoevaporation. As this cosmic fog is burned away, it exposes the far denser, more resilient pockets of material within the pillars. These are the embryonic cocoons of new stars, the stellar nurseries that were hidden from view. So, what we witness is not just destruction, but a dramatic and beautiful act of revelation, where the intense energy of one generation of stars peels back the curtain to show us where the next generation is being born from the very same cosmic material. Another of the sky's beautiful and strange nurseries is the Red Rectangle Nebula, which, despite its name, is not a rectangle at all.
Instead, it forms a spectacular glowing X shape with distinct rungs that look like a celestial ladder. This bizarre geometry is a puzzle that points to a complex stellar dance at its center. Astronomers believe a pair of stars, a binary system, is responsible for this unique structure. One of the stars is in its final stages of life, puffing its outer layers of gas and dust into space. This material doesn't simply expand outwards in a sphere, but first forms a thick, donut-shaped ring, or torus, around a star system's equator. The companion star then likely shoots out powerful jets of gas from its poles, which slam into this surrounding torus. These jets carve out two vast, cone-shaped cavities in the dust. And when we view this structure from the side, the glowing edges of these cones create the striking X shape, a truly unique and beautiful piece of relaxing cosmic architecture. Shifting our gaze to a star much closer to home, the famous red supergiant Betelgeuse gave astronomers quite a scare in late 2019. It began to dim dramatically, losing more than 2/3 of its usual brightness, an event now known as the Great Dimming. Many speculated this was the final prelude to a spectacular supernova explosion, an event that would be visible even in our daytime sky. However, after careful study with telescopes like Hubble, the true cause was found to be something a little less dramatic, but no less amazing. Betelgeuse hadn't started to collapse. Instead, it had experienced a massive surface convection event, essentially a stellar burp. It ejected a colossal cloud of hot gas into space, and as this cloud traveled away from the star, it cooled and condensed into a vast screen of obscuring dust. This dust cloud simply blocked our view of Betelgeuse for a few months, like a temporary celestial curtain before it dissipated into space. This calming fact about astronomy shows us that even the most violent-seeming stars have complex weather of their own. While we wait for Betelgeuse, other stellar explosions serve a much different, more precise purpose. A specific kind of explosion, called a Type 1a supernova, has become one of the most important tools in all of cosmology. These supernovae are not caused by the collapse of a single massive star, but rather occur in binary systems where a small, dense white dwarf star siphons material from a companion. Once the white dwarf reaches a precise, critical mass, about 1.4 times that of our Sun, it triggers a runaway thermonuclear reaction that blows it apart. Because they all explode at this exact same mass, the explosions all have the same intrinsic brightness. They are what astronomers call standard candles. By observing how dim one of these supernova appears from Earth, we can calculate its distance with incredible accuracy. It was by measuring the distances to these faraway explosions that astronomers made the Nobel Prize-winning discovery that the expansion of the universe is not slowing down, but is actually accelerating, driven by the mysterious force we now call dark energy. Imagine for a moment being able to hear the death of a star. While space is a vacuum and sound cannot travel in the conventional sense, scientists have developed a way to experience these cosmic cataclysms through a process called data sonification. They can take the immense streams of information gathered from a supernova, the changing brightness of its light over weeks, the burst of ethereal neutrinos that precedes the explosion, and even the subtle ripples in space-time known as gravitational waves, and translate these datasets into sound waves. The result is a haunting and complex symphony. The rising and falling pitch might represent the light curve, while a percussive crash could signify the core collapse, and a shimmering, high-frequency chirp could be the gravitational wave signal. This allows us to perceive these silent, distant events with a different sense, transforming pure data into an auditory journey through one of the most powerful events in the universe. It makes you wonder, if you could listen to any single event in the cosmos,
what celestial soundscape would you choose to drift off to sleep to? From the explosive end of some stars, we turn to the quiet, gravitational collapse of others, leading to black holes. There is a common and dramatic misconception that black holes are cosmic vacuum cleaners, relentlessly sucking up everything in their vicinity. In reality, their gravitational pull behaves just like any other object of the same mass, unless you get incredibly close. For instance, if our Sun were to suddenly be replaced by a black hole with the exact same mass, a startling but useful thought experiment, the orbits of Earth and all the other planets would remain completely unchanged. We would not be pulled in or fall into a new trajectory. We would continue to orbit the black hole just as we orbit the Sun today. Of course, without the Sun's light and heat, Earth would freeze over, but the gravitational effect at our distance would be identical. A black hole's extreme gravitational effects only dominate in its immediate vicinity, very near its boundary of no return, the event horizon. Once something does cross that event horizon, especially for a smaller stellar mass black hole, it faces a truly strange fate known as spaghettification. This isn't just a colorful term, it describes a very real physical process. It's caused by an extreme tidal force, which is the difference in gravitational pull across an object. As an object, say a drifting asteroid, falls feet first towards the black hole, the gravitational pull on its nearest point is exponentially stronger than the pull on its farthest point. This immense differential in force would stretch the object vertically, pulling it longer and longer, while simultaneously compressing it horizontally from all sides. This process would continue relentlessly, stretching any form of matter into a long, thin stream of its constituent atoms, like a strand of spaghetti being fed into the black hole's center. It is one of the most extreme examples of gravity's power in the known universe, a quiet and inevitable unraveling of matter itself. Counterintuitively, this fate of being instantly spaghettified is not a universal rule for all black holes. For the true giants of the universe, the supermassive black holes that reside at the centers of galaxies, the experience of crossing the event horizon would be surprisingly gentle. This is because the size of the event horizon is proportional to the black hole's mass. A supermassive black hole, like Sagittarius A star in our own Milky Way, is so enormous that its event horizon is millions of kilometers wide. Because of this vast scale, the curvature of space-time at the boundary is much flatter, and the tidal forces, the difference in gravity from one end of an object to the other, are remarkably weak. An astronaut falling into such a black hole could theoretically cross the event horizon completely intact, without feeling any immediate stretching or discomfort. The point of certain spaghettification would still come, but it would be much deeper inside, far past the point of no return. The feeding habits of black holes are also proving to be far messier and more complex than we once imagined. When a star wanders too close to a supermassive black hole, it is shredded by the intense tidal forces in what's called a tidal disruption event. This process releases a brilliant flare of radiation as the star's material is heated up and partially consumed by the black hole. We used to think this was a single, dramatic meal. However, astronomers were recently stunned when they observed a black hole several years after it had torn apart a star suddenly emit another enormous plume of material at nearly half the speed of light. It seems the black hole didn't swallow everything from its initial meal neatly. Some of the stellar material was left in orbit, and years later, it finally fell back towards the black hole, causing this delayed outburst. It was as if the black hole had burped up the leftovers from a meal it had years prior, a relaxing reminder that even in astronomy, cosmic events can unfold on surprisingly human-like timescales. Finally, we come to a profound realization that reshapes our very understanding of these objects. Black holes are not entirely black, nor are they eternal.
The great physicist Stephen Hawking proposed that, due to the strange rules of quantum mechanics, black holes must slowly leak energy back into the universe. This phenomenon, now known as Hawking radiation, originates right at the edge of the event horizon. In the vacuum of space, pairs of virtual particles, one of matter, one of antimatter, are constantly popping into existence and then immediately annihilating each other. If a pair is created right at the event horizon, it's possible for one particle to fall into the black hole while the other escapes into space. To an outside observer, it appears as though the black hole is emitting a faint glow of particles. This escaping particle carries away a minuscule amount of the black hole's mass and energy. Over unfathomable timescales, trillions upon trillions of years, this slow leak will cause the black hole to evaporate completely until nothing is left. Our own Milky Way is not a peaceful island in the cosmos, but a patient cannibal. It achieved its grand spiral form by consuming smaller galaxies over billions of years. When a dwarf galaxy strays too close, the Milky Way's immense gravity begins to pull it apart in a process called tidal stripping. The smaller galaxy is stretched and unraveled like a ball of cosmic yarn, its stars spilling out into long, graceful arcs that wrap around our own galaxy. These are known as stellar streams, and astronomers have mapped dozens of them, each one a ghostly trail marking the final path of a devoured galaxy. The Sagittarius stream, for example, is a colossal ribbon of stars that encircles the Milky Way twice, the remnant of a dwarf galaxy that is still in the process of being torn asunder. These acts of galactic cannibalism are not violent collisions, but slow, inevitable mergers that build larger galaxies from the remnants of smaller ones, a fundamental process of growth in the universe. And this cosmic cycle of consumption will continue, with our own galaxy set to be part of the grandest merger in our local history. In about 4.5 billion years, the Milky Way will collide with its largest neighbor, the Andromeda Galaxy. But this will not be a cataclysm of crashing stars. Instead, it will be an astonishingly slow and graceful dance of gravity. The space between stars is so vast that it is incredibly unlikely any two stars will actually hit each other. Instead, the two grand spirals will pass through one another, their gravitational fields flinging stars into new, sweeping orbits. Over hundreds of millions of years, they will pull back together, passing through each other again and again. With each pass, their beautiful spiral structures will be disrupted and tangled, until eventually, after nearly 1 billion years of this cosmic ballet, they will settle into a single, enormous, and more chaotic galaxy, a giant elliptical galaxy that some astronomers have already nicknamed Milkomeda. The night sky for any future inhabitants will be spectacularly transformed. The shapes that galaxies take, like the spirals of the Milky Way and Andromeda, or the elliptical form of their future merger, were famously catalogued by Edwin Hubble in a diagram known as the Hubble tuning fork. For a long time, many people assumed this was an evolutionary diagram, showing how neat, round elliptical galaxies might flatten and spin out into elegant spirals over time. But this is a complete misconception. Hubble himself was careful to state that the diagram was purely a classification tool based on appearance, not a timeline of galactic life. There is no evidence that ellipticals evolve into spirals. In fact, the evidence often points in the opposite direction, with spiral galaxies like our own merging to become giant ellipticals. The diagram simply organizes them by their visual morphology, from the featureless, ball-like ellipticals to the tightly wound and then more open-armed spirals, with a separate branch for spirals that feature a distinct bar of stars through their center. While Hubble's diagram covers the most common galactic shapes, the universe is filled with stranger varieties that defy easy classification.
Among the most ethereal are the ultra-diffuse galaxies, or UDGs. These are cosmic ghosts, galaxies as large as the Milky Way, stretching for tens of thousands of light years, yet containing only 1% as many stars. They are so faint and spread out that you can see other, more distant galaxies right through them. Their existence is a profound puzzle. How could a collection of stars become so enormous without being more densely packed? One leading theory is that they are failed Milky Way-type galaxies, where some early, violent burst of star formation blew away most of the remaining gas, preventing any more stars from being born and allowing the existing ones to drift far apart. Stranger still, they appear to be held together by an immense amount of dark matter, far more than their sparse stars would suggest, making them natural laboratories for studying this mysterious substance. Our own Milky Way, upon closer inspection, has its own special features not immediately apparent from our vantage point within it. We don't live in a simple spiral galaxy, but a barred spiral galaxy. This means that running through the dense central bulge of our galaxy is a colossal, tightly packed bar of stars, estimated to be about 27,000 light-years in length. This stellar bar isn't just a static feature. It rotates like a giant propeller in the galaxy's heart, and its immense gravity has a profound effect on the surrounding disk. It acts like a cosmic traffic director, funneling vast streams of interstellar gas and dust from the spiral arms inward toward the galactic center. This constant supply of fuel is what ignites furious bursts of star formation in the core and ultimately feeds the supermassive black hole Sagittarius A star that lurks there. For decades, the bar's existence was debated, as it was impossible to see directly through the thick dust of the galactic plane. But infrared surveys that can pierce the veil have now mapped its structure in detail. Extending far beyond the central bar and invisible to the naked eye are two of the largest and most mysterious structures in our entire galaxy, the Fermi bubbles. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, these are a matched pair of colossal bubbles blowing out from the galactic center. Each one stretches 25,000 light-years perpendicular to the galaxy's disk, one rising above and one dropping below, forming a giant hourglass shape that glows in high-energy gamma rays and X-rays. Together, they span a distance greater than half the width of the Milky Way's visible disk. The leading theory for their origin is that they are the shock waves from an unimaginably powerful eruption that took place millions of years ago. Perhaps our central supermassive black hole, Sagittarius A star, devoured a massive star cluster or gas cloud, releasing a titanic blast of energy that inflated these ghostly bubbles, which continue to expand into intergalactic space today. As vast as our galaxy and its structures are, the Milky Way itself is not stationary. It is being pulled through space by a force we cannot fully see. Our entire local group of galaxies, including Andromeda and dozens of smaller ones, is hurtling along at over 2 million kilometers per hour towards a specific point in the sky. This destination is a gravitational anomaly known as the Great Attractor. For decades, its exact nature was a mystery because it lies in a direction obscured by the dense plane of our own galaxy, an area called the Zone of Avoidance. We now know this attractor is not a single object, but the central gravitational point for a truly immense supercluster of galaxies called Laniakea, which means immeasurable heaven in Hawaiian. Our Milky Way is not at the center of this structure, but on its distant outskirts, like a piece of driftwood being pulled into a vast, slow-moving cosmic whirlpool spanning over 500 million light-years. While some galaxies are defined by their immense size or strange emptiness, others are notable for their sheer creative vigor. A fascinating class of these are the green pea galaxies. They earned their quirky name because in the automated images of the Sloan Digital Sky Survey, they appeared as small, unresolved, and distinctly green dots, looking quite unlike typical galaxies. This green glow is the signature of intensely ionized oxygen, a clear sign that these small, compact galaxies are undergoing star formation at a shockingly furious rate, far more intense than in the Milky Way. They are essentially galactic nurseries on overdrive. Astronomers are so interested in them because they are believed to be excellent modern-day analogs for the types of small, fiery galaxies that existed in the early universe. Studying these green peas gives us a precious window into the cosmic dawn, helping us understand how the first generations of stars and galaxies produced enough radiation to burn off the primordial fog of neutral hydrogen that once filled the cosmos. Even our closest galactic neighbors hold deep secrets that we are only just uncovering. The large and small Magellanic Clouds, visible as faint smudges in the southern night sky, were long assumed to be loyal satellite galaxies, having orbited the Milky Way for billions of years. However, precise measurements of their velocity using the Hubble Space Telescope have turned this idea on its head. The data suggest they are moving far too fast to be in a stable, long-term orbit. Instead, it now appears that they are newcomers to our neighborhood, making their very first pass by the Milky Way. This changes everything about how we interpret them. Their irregular shapes and bursts of star formation were once thought to be the result of eons of gravitational harassment by our galaxy. Now, it seems these features are from their own history, and we are just now beginning to witness the slow, dramatic process of their capture and eventual absorption by the Milky Way. Just as we are discovering our neighbors may be new, we are also finding old neighbors that have been hiding in plain sight. This is because some galaxies are made almost entirely of the one thing we cannot see: dark matter. A prime example is Antlia 2, a ghostly dwarf galaxy discovered orbiting the Milky Way. It is enormous in size, about as large as the Large Magellanic Cloud, yet it is thousands of times fainter. It is so incredibly diffuse and sparsely populated with stars that astronomers have called it a ghost galaxy. It remained undetected for so long despite its size because its few stars are spread over a vast area of the sky. The only thing holding this fragile collection of stars together across such a huge expanse must be a truly gigantic halo of dark matter. Antlia 2 radically challenges our models of galaxy formation, suggesting that perhaps the universe is filled with these massive, dark matter-dominated specters that we have only just begun to find. It makes you wonder what else might be lurking, almost invisibly, in the darkness between the bright islands of stars we can see. As you settle into sleep, do you ever find it more relaxing to think about the vast, dark, quiet spaces in the universe, or the bright, energetic stars and galaxies? Looking out across the cosmos, we can still see the afterglow of its creation. This faint, uniform glow filling all of space is called the cosmic microwave background radiation. It is the oldest light in the universe, a relic from a time when the entire cosmos was a hot, dense, opaque fog, just 380,000 years after the Big Bang. As the universe expanded and cooled, this fog cleared, and the light that was trapped within it was finally set free to travel across space for eternity. Its discovery in 1965 was purely accidental. Two radio astronomers, Penzias and Wilson, were trying to eliminate a persistent background hiss in their antenna, even cleaning out pigeon droppings, before realizing the noise was coming from everywhere in the sky. This ancient echo of creation, now cooled to just 2.2 Kelvin, 7 degrees above absolute zero, provided the single most powerful piece of evidence for the Big Bang, a faint whisper from the dawn of time itself. While this cosmic afterglow is astonishingly uniform, it contains tiny temperature fluctuations, seeds of the future galaxies. Yet, within these random-seeming patterns lies a profound and unsettling anomaly that some have called the axis of evil. When mapped in detail, the largest-scale patterns in the background radiation don't appear to be random at all. Instead, they seem to be strangely aligned with the plane of our own solar system, the path the Earth takes around the Sun.
There is absolutely no known reason why a feature from the very early universe, long before the Sun or Earth even existed, should be aligned with our little neighborhood in this way.
It implies a connection between our local patch of space and the largest observable structures in the cosmos, a preferred direction that defies the core cosmological principle that the universe is the same in all directions. It remains one of cosmology's most perplexing mysteries. Before light could travel freely through the cosmos, the universe was filled with a dense plasma, and through this primordial soup, sound waves traveled. These were not sound waves you could hear, but vast pressure waves, known as baryon acoustic oscillations, rippling outwards from tiny, dense spots in the early universe. These sound waves traveled for hundreds of thousands of years until the universe cooled enough to become transparent. At that moment, the waves simply froze in place, leaving a faint, spherical imprint on the distribution of matter. Think of it like a ripple in a pond, suddenly flash frozen. Billions of years later, these frozen ripples influenced where galaxies would form, creating a subtle preference for galaxies to be separated by a specific distance, about 500 million light-years. This distance acts as a standard ruler for astronomers, allowing them to measure the expansion history of the universe by observing the patterns in how galaxies are clustered together today. The echoes of these ancient waves helped shape the grand cosmic web of galaxies, but even within this web, there are monumental, unseen forces at play. Our own Milky Way galaxy, along with the entire Laniakea supercluster containing 100,000 other galaxies, is being pulled at over 2 million kilometers per hour towards a mysterious and colossal gravitational anomaly. This destination is known as the Great Attractor. We cannot see it directly, as it lies in a region of the sky known as the Zone of Avoidance, where the dust and stars of our own Milky Way's disk block our view. For decades, its true nature was a complete enigma. We now know it is the central gravitational point of our vast supercluster, a dense concentration of galaxy clusters and unseen mass, exerting an inescapable pull on a scale so large it is almost impossible to comprehend. A hidden capital city in our cosmic empire. The immense gravitational pull of structures like the Great Attractor points to a substance that dominates the universe yet remains completely invisible: dark matter. It is a common misconception to think of it as simply being dark in the way a black cat is dark at night. The truth is far stranger. Dark matter is not dark, it is transparent. It does not interact with light or any form of electromagnetic radiation. It doesn't absorb, reflect, or emit light, which is why we cannot see it with any telescope. It also doesn't interact with normal matter. Trillions of dark matter particles are likely streaming through your body right now, passing through the Earth and out the other side as if neither you nor the planet were even there. Its existence is known to us only through its immense gravitational influence, holding galaxies together and bending the light from distant objects, an invisible skeleton upon which the visible universe is built. Does thinking about these vast, invisible structures make space feel more mysterious, or perhaps more peaceful to you as you drift toward sleep? The most compelling proof of this ghostly substance comes from a celestial event known as the Bullet Cluster.
This is actually two galaxy clusters that have passed directly through one another in a cataclysmic collision that occurred over millions of years. Using telescopes, we can see the normal matter, the hot, glowing gas from each cluster, colliding and slowing down, creating a massive, bullet-shaped cloud of superheated gas in the center. However, by using gravitational lensing to map where the mass is, astronomers found something astonishing. Most of the mass from the two clusters didn't slow down at all. It passed right through the collision without interacting, creating two separate, invisible clumps of mass on either side of the hot gas. This clear separation of visible, interacting matter from the non-interacting, gravitational mass is the smoking gun for dark matter, proving it is a real, separate substance that glides through the cosmos like a ghost. While dark matter's gravity pulls the universe together, an even more mysterious force is actively pushing it apart. For most of the 20th century, astronomers assumed the universe's expansion, started by the Big Bang, must be slowing down due to the mutual gravitational pull of all the matter within it. But in 1998, two separate teams studying distant supernovae made a discovery that shattered all expectations. They found that these distant exploding stars were fainter and therefore farther away than they should have been if the expansion was slowing down. The only explanation was that the expansion of the universe is not slowing down, it is accelerating. Some unknown repulsive force is overwhelming gravity on the largest scales, pushing everything apart at an ever-increasing rate. This force was named dark energy, and its discovery was so profound it completely rewrote our understanding of the universe's ultimate fate. The existence of dark energy brings back an idea that Albert Einstein once called his biggest blunder. When he first formulated his theory of general relativity, his equations suggested the universe must be either expanding or contracting. To force it to be static, which was the prevailing belief at the time, he added a fudge factor, an inherent energy of space itself, which he called the cosmological constant. When the universe was later proven to be expanding, he discarded the idea. Yet now, this same concept has been revived as the leading explanation for dark energy. The problem is, when our best theories in quantum physics try to calculate the value of this energy, they predict a number that is staggeringly large, a 1 followed by 120 zeros larger than what we actually observe. This discrepancy, known as the cosmological constant problem, is perhaps the single greatest disagreement between theory and observation in the history of science. If this mysterious dark energy continues to dominate, it could lead to a spectacular and terrifying end for the universe known as the Big Rip. This hypothesis imagines a future where the repulsive force of dark energy grows stronger over time. In this scenario, its outward push would eventually become so powerful it would overcome all other forces. In the final tens of billions of years, it would first tear apart the cosmic web, pushing galaxy clusters away from each other. Then, with about 60 million years left, it would overcome gravity within galaxies, unbinding the Milky Way and sending its stars flying into the void. In the final months, solar systems would be dismantled. And in the last fraction of a second, the electromagnetic forces holding atoms together would fail, and every single atom in the universe would be ripped apart into elementary particles, ending space and time in a final, complete dissolution. For now, these two great cosmic unknowns, dark matter and dark energy, perfectly balance the universe on a knife's edge. Together with normal matter, their combined density is incredibly close to a specific value known as the critical density. This precise density means that the overall geometry of the universe is flat. On a cosmic scale, this means that if you were to draw two parallel beams of light, they would remain parallel forever, never converging or diverging.
The angles of any giant cosmic triangle you could draw between three distant galaxies would add up to exactly 180 degrees. This flatness is highly unlikely to have occurred by chance. It is best explained by the theory of cosmic inflation, which proposes that the universe underwent a period of hyper-accelerated expansion in its very first instant, stretching and smoothing any initial curvature out of existence, leaving behind the vast, geometrically simple cosmos we see today. Our quest to understand the cosmos has led us to create some of the most ambitious messages and magnificent instruments ever conceived. In 1974, from the Arecibo Observatory in Puerto Rico, humanity sent its first intentional, high-powered message to the stars. It was a simple, 3-minute broadcast of binary code aimed at Messier 13, a dense globular cluster of stars some 25,000 light-years away. If decoded and arranged into a grid, the message forms a simple pictograph containing fundamental information about us. It depicts our base 10 counting system, the atomic numbers of essential elements like hydrogen and carbon, the formulas for the sugars and bases in our DNA, and a graphical representation of the DNA double helix itself. Alongside these is a simple stick figure of a human, our average height, the population of Earth at the time, a map of our solar system with Earth offset, and a final image of the Arecibo telescope that sent the message. It was a greeting card to the galaxy, a profound statement of our existence cast into the void, though any potential reply would take 50,000 years to complete the round trip. Following this broadcast, a more tangible message was launched aboard the Voyager 1 and 2 spacecraft in 1977. Known as the Golden Record, it is a gold-plated copper phonograph disc, an analog time capsule designed to last for 1 billion years in the cold of interstellar space. Curated by a committee led by Carl Sagan, the record contains a rich tapestry of life on Earth. It holds 115 images encoded in analog form, showcasing scientific diagrams, human anatomy, and scenes from nature and daily life. It also carries a collection of sounds, from the crash of surf and the cry of a whale to the rumble of a train. The musical selection is deliberately eclectic, featuring everything from Bach and Beethoven to Chuck Berry's Johnny B. Good, and traditional music from around the globe. Most poetically, it begins with greetings in 55 different languages, ancient and modern. The record's protective cover is etched with instructions on how to play it and a pulsar map, a celestial guidepost pinpointing our sun's location relative to 14 pulsars, allowing any intelligent finder to locate our world in both space and time. While these messages travel outward, our most profound discoveries have come from the signals we collect from the universe. Perhaps no single observation has redefined our perspective more than the Hubble Deep Field. In 1995, astronomers decided to take an immense gamble. They pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky near the Big Dipper's handle, a spot so dark and unremarkable it was chosen specifically for its lack of known stars. For 10 consecutive days, over 342 separate exposures, Hubble stared into this abyss, collecting every faint photon it could. The result was breathtaking and world-changing. The image was not empty at all. It was filled with over 3,000 distinct galaxies. Each faint smudge of light was an entire island universe, some so distant that their light had been traveling for over 12 billion years to reach us. It was a core sample of the universe, revealing a cosmic history stretching back to near the very beginning, and it proved that the universe is uniformly teeming with galaxies, even in its darkest, most unassuming corners. To peer even further back in time, to the universe's first dawn, required a new kind of observatory, the James Webb Space Telescope. One of its most critical and complex components is its enormous sun shield. This 5-layer shield is the size of a tennis court, yet each layer is made from a specialized plastic called captain that is as thin as a human hair. Its purpose is to protect the telescope's sensitive instruments from the heat and light of the Sun, Earth, and Moon. As heat radiates from the Sun, it is reflected by the first layer. The heat that gets through is then reflected by the second, and so on. The vacuum of space between each layer acts as a perfect insulator. This passive cooling system is so efficient that while the sun-facing side of the shield can reach temperatures of over 230 degrees Fahrenheit, the side housing the scientific instruments remains at an astonishingly cold -390 degrees Fahrenheit. This extreme temperature difference is what allows Webb to detect the faint, ancient infrared light that has traveled for over 13 billion years. 5 billion years across the expanding universe. Getting these incredible observatories and probes to their destinations often requires a little help from the cosmos itself, using a technique called a gravity assist. This maneuver, sometimes called a slingshot, allows a spacecraft to steal a tiny amount of a planet's orbital energy to gain incredible speed.
As a probe like Voyager approaches a giant planet such as Jupiter, it falls into the planet's immense gravity well, accelerating dramatically. It then swings around the planet and is flung back out, but now its speed relative to the Sun is much greater. In exchange, the planet's own orbital speed is reduced by a minuscule, completely immeasurable amount.
This cosmic billiard shot is the reason missions to the outer solar system are possible. It saves years of travel time and vast amounts of fuel, allowing us to send probes on grand tours of the solar system that would otherwise be beyond our technological reach, using the very laws of celestial mechanics to our advantage. Not all observatories use mirrors or lenses to capture light. Some use a cubic kilometer of solid ice at the South Pole to hunt for the universe's most elusive particles. This is the Ice Cube Neutrino Observatory. It is designed to detect high-energy neutrinos, often called ghost particles, because they have almost no mass and can pass through entire planets without interacting with anything. To catch one, scientists have embedded over 5,000 light sensors deep within the Antarctic ice sheet. There, in the profound darkness, they wait. On the rare occasion that a neutrino from a distant supernova or a supermassive black hole collides with an atom in the ice, it produces other particles that, in turn, generate a faint cone of blue light known as Cherenkov radiation. The sensors detect this fleeting flash, and by analyzing the pattern and timing of the light, scientists can reconstruct the neutrino's energy and the direction it came from. In this way, the entire Earth becomes part of the telescope, filtering out other cosmic rays and allowing us to see the universe in a way that is totally invisible to all other forms of astronomy. The precision required for deep space exploration is almost beyond comprehension, perfectly exemplified by the New Horizons mission to Pluto. Launched in 2006, it was the fastest spacecraft ever to leave Earth, but its journey to the edge of the solar system would still take 9.5 years. Navigators had to aim for a spot in space where Pluto would be nearly a decade later. They had to account for every gravitational nudge from the Sun and planets, and even the tiny, persistent push from sunlight itself on the spacecraft's body. Over a journey of more than 3 billion miles, their calculations were so exact that when New Horizons finally flew past the dwarf planet in 2015, it arrived just 72 seconds earlier than planned and missed the center of its target window by a mere 43 miles. It was the equivalent of hitting a specific moving golf ball in Los Angeles with another golf ball launched from New York City. This stunning navigational feat gave humanity its first ever close-up look at the mysterious, icy world of Pluto. While New Horizons explored the frigid outer reaches, the Parker Solar Probe embarked on a journey to the most extreme environment in the solar system, the Sun's own atmosphere. To survive flying through the solar corona, where temperatures can soar to millions of degrees, the probe is protected by an extraordinary heat shield. Called the Thermal Protection System, it is a disk of advanced carbon composite material just 4.5 inches thick. The front face of this shield glows red hot, enduring temperatures of about 2,500 degrees Fahrenheit, hot enough to melt steel. Yet just inches behind it, the probe's scientific instruments remain at a comfortable room temperature of around 85 degrees. The shield is made of a lightweight carbon foam core sandwiched between two superheated carbon plates and is coated with a special white ceramic paint to reflect as much of the sun's energy as possible. This technology allows Parker to fly closer to our star than any spacecraft in history, sampling particles and magnetic fields to solve long-standing mysteries about how the solar wind is born. Most of our great observatories are either perched atop remote mountains or floating freely in the vacuum of space. But one unique telescope operates from the inside of a jumbo jet. SOFIA, the Stratospheric Observatory for Infrared Astronomy, is a heavily modified Boeing 747 SP aircraft carrying a massive 17-ton, 2.7-meter reflecting telescope. During its 10-hour overnight flights, a huge door in the fuselage slides open, exposing the telescope to the sky at altitudes up to 45,000 feet. The reason for this incredible feat of engineering is Earth's atmosphere, specifically the water vapor within it. Water vapor absorbs most of the infrared radiation that comes from space, making the universe at these wavelengths invisible from the ground. By flying high above 99% of this obscuring atmospheric water, SOFIA gains a crystal clear view. This allows astronomers to study phenomena they couldn't otherwise see, from the birth of stars inside dense cosmic clouds to the complex chemistry occurring in the atmospheres of other planets, all before coming in for a landing at dawn. Finally, some of our most iconic observatories are not single instruments at all, but vast arrays working in unison. The Carl G.C. Jansky Very Large Array, or VLA, spreads 27 monumental radio antennas across the plains of New Mexico. Each dish is 82 feet in diameter and weighs 230 tons. Through a technique called interferometry, the signals from all 27 antennas are combined, allowing them to function as a single gigantic telescope with a resolution far greater than any one dish could achieve alone. What makes the VLA truly special is its configurability. The antennas are positioned along a Y-shaped network of railway tracks, with each arm of the Y stretching for 13 miles. By moving the antennas along these tracks, astronomers can change the size of the array. Spreading them far apart creates a telescope up to 22 miles wide, perfect for zooming in on fine details. Grouping them close together provides a wider field of view. This ability to essentially change its own zoom lens has made the VLA one of the most productive radio telescopes in history. Have you ever visited a place that felt so vast and otherworldly it could have been from a science fiction movie? Some of the most profound discoveries in astronomy concern worlds far beyond our solar system, and not all of them orbit a star. There are countless rogue planets, also known as interstellar planets, that drift through the vast, cold darkness of space, unbound to any stellar system. Ejected from their parent systems during their turbulent formation, these lonely wanderers travel the galactic wilderness alone. You might imagine them as frozen, lifeless spheres of rock and ice, but that isn't necessarily the case. A sufficiently large rogue planet with a thick hydrogen atmosphere could trap enough of its own internal heat, generated by radioactive decay in its core, to maintain liquid water on its surface. Life in such a place wouldn't know sunlight, but could potentially thrive in the planet's geothermally powered oceans, a scenario that dramatically expands the potential real estate for life in the cosmos. It suggests that a planet doesn't need a parent star to be a cradle for life, only its own internal warmth and the right ingredients. As you listen to these calming facts about distant, lonely worlds, what is the most comforting thought you have about our own quiet place in the universe? When we do find planets around other stars, their atmospheres can be far more extreme and alien than anything imagined in science fiction. Astronomers have discovered worlds where the weather is truly bizarre. Take the exoplanet HD 18973b, a deep blue gas giant that looks serene from a distance. Up close, however, its skies are a nightmare. Its winds howl at over 5,000 miles per hour, 7 times the speed of sound. And it doesn't rain water, it rains molten glass sideways. The planet's blue hue comes not from oceans, but from silicate particles in its atmosphere scattering light. On another world, WASP 76b, it gets so hot on its day side that iron vaporizes into the atmosphere. These iron clouds then drift over to the cooler night side of the planet, where the temperature drops enough for the iron to condense and fall back down as a rain of liquid metal. These discoveries remind us that our earthly weather, even at its most severe, is remarkably gentle compared to the atmospheric violence found elsewhere in the galaxy. One of the most exciting exoplanetary systems discovered to date is TRAPPIST-1, located about 40 light-years away. It features not 1 or 2, but 7 Earth-sized rocky planets orbiting a tiny, cool star known as an ultra-cool dwarf. What makes this system so remarkable is that at least 3 of these planets orbit within the star's habitable zone, the region where temperatures could be just right for liquid water to exist on their surfaces. The planets are packed incredibly close together, far closer than the planets in our own solar system. If you were standing on one of the TRAPPIST-1 worlds, the other planets would appear in the sky not as distant points of light, but as large disks, some as big as our own moon. Because they are so close to their faint star, they are all likely tidally locked, meaning one side of each planet perpetually faces the star while the other is locked in eternal darkness, creating permanent day and night zones. This phenomenon of tidal locking gives rise to a fascinating theoretical type of world known as an eyeball planet. Imagine a planet where one hemisphere is forever baked by its star, creating a vast, scorched desert, while the opposite hemisphere is a frozen wasteland of endless night. Life would be impossible in these extreme zones. However, in the region between them, the Terminator line, where perpetual twilight exists, conditions could be perfect. This ring of permanent dawn or dusk could host a band of stable, mild temperatures where liquid water could flow in vast rivers or oceans. The strong winds generated by the extreme temperature difference between the day and night sides would create a global weather system, potentially distributing heat and creating a stable climate within this narrow habitable ring. For any life that evolved here, the sun would be a constant, unmoving fixture on the horizon, neither rising nor setting, creating a world of eternal sunset and unique evolutionary pressures. Our ability to study these distant worlds has been revolutionized by the James Webb Space Telescope. Its power lies not just in taking beautiful images, but in a technique called transmission spectroscopy. When an exoplanet passes in front of its host star from our point of view, a tiny fraction of the starlight filters through the planet's atmosphere. Different gases in that atmosphere absorb specific wavelengths or colors of light. By analyzing the starlight that reaches the telescope, Webb can identify these missing wavelengths and create a chemical fingerprint of the planet's atmosphere. This is how we are beginning to detect the presence of water vapor, methane, carbon dioxide, and other compounds on worlds light years away. This technique is our primary tool in the search for biosignatures, gases like oxygen or methane in specific combinations that could indicate the presence of biological processes. Webb is essentially sniffing the air of alien worlds from across the galaxy. This search for life is often guided by a thought experiment known as the Drake equation. Formulated by astronomer Frank Drake in 1961, it's not meant to provide a definitive answer, but rather to organize our thinking. The equation multiplies a series of factors to estimate the number of active, communicative, extraterrestrial civilizations in the Milky Way. It considers variables like the rate of star formation, the fraction of those stars with planets, the number of planets that could support life, the fraction of those where life actually arises, the fraction of life that develops intelligence, and the fraction that develops technology to send detectable signals into space. Finally, it considers the length of time such a civilization might broadcast those signals. While many of these variables are complete unknowns, the equation serves as a powerful reminder of both the vast possibilities and our profound ignorance about our place in the cosmos. The Drake equation's optimistic possibilities lead directly to one of astronomy's most troubling questions, the Fermi paradox. Physicist Enrico Fermi famously posed the question during a lunch conversation. Given the age and size of the universe and the high probability of Earth-like planets, intelligent life should be common. So, if the galaxy is teeming with civilizations, some of which should be millions of years older and far more advanced than us, why have we found no evidence of them? Where is everybody? This great silence is deeply puzzling. Dozens of potential solutions have been proposed. Perhaps we are the first intelligent species to arise. Perhaps interstellar travel is simply too difficult. Or perhaps there is a great filter, some inevitable challenge or catastrophe that prevents civilizations from surviving long enough to colonize the galaxy, a filter that we ourselves have yet to face. While we search for planets like our own, it's possible we're not looking for the best real estate. Scientists have conceived of superhabitable planets, worlds that could be even better suited for the emergence and evolution of complex life than Earth. Such a planet might orbit a K-dwarf star, which is smaller and longer-lived than our Sun, providing billions more years of stability for life to flourish. It might be slightly larger and more massive than Earth, giving it a stronger magnetic field to shield against cosmic radiation and enough gravity to retain a thicker, more protective atmosphere. It might have shallower oceans, promoting greater biodiversity in sunlit coastal waters and a slightly warmer average temperature. The existence of such worlds is purely theoretical, but it challenges our anthropocentric view that Earth is the pinnacle of habitability. There may be worlds out there where life is not just possible, but far easier. Amidst the silence, there is one signal that continues to haunt and inspire the search for extraterrestrial intelligence. On August 15, 1977, the Big Ear radio telescope at Ohio State University detected a powerful, narrow-band radio signal lasting for 72 seconds. It came from the direction of the constellation Sagittarius and bore all the expected hallmarks of an artificial, non-terrestrial transmission. Astronomer Jerry Emin, who discovered the anomaly while reviewing the data days later, was so astonished that he circled the signal on the computer printout and wrote "Wow" in the margin. The signal was incredibly strong and occupied a frequency band that is internationally protected for astronomical use. Despite numerous attempts to redetect it from the same patch of sky, the "wow" signal has never been heard again. It remains the single most compelling and most mysterious potential candidate for a message from an alien civilization ever recorded. This brings us to a final, humbling thought about the Great Silence. Perhaps it is not empty, but intentional. The zoo hypothesis suggests that advanced extraterrestrial civilizations are aware of us but deliberately choose not to make contact, observing us from a distance as we would observe animals in a wildlife preserve, allowing our natural development to proceed without interference. A related idea is that advanced civilizations, aware of potential cosmic dangers, adopt a policy of silence, listening intently but never broadcasting their own location to avoid attracting unwanted attention. In this scenario, the universe isn't empty, but full of quiet, cautious neighbors. It suggests that our first contact may not come from a grand announced arrival, but from the slow, patient work of listening to the whispers hidden within the cosmic static, finally understanding that we may not be alone, but simply the youngest and loudest species in a very old and quiet galactic neighborhood. Thank you for joining this calming journey through the wonders of astronomy. If you've enjoyed these relaxing facts and would like more sleep-friendly science to drift off to, please consider subscribing and returning for our next exploration. Until then, may your thoughts be as vast and as peaceful as the night sky itself.